Bismillahirrahmanirrahim. In this lecture, we will discuss the dimensions of physical quantities. In our lecture, we will start from the definition of dimensions, then we will discuss the dimensions of base quantities. We will also talk about the sets of dimensions that we use in mechanics, electricity and magnetism, and in thermodynamics. These are three major groups of physics. In each group, we will talk about the set of dimensions that is used. And then we will talk about the dimensions of derived quantities, dimensions of supplementary quantities, some features of dimensions, applications of dimensions, and finally, we will talk about the drawbacks of dimensions. We can say it as drawbacks or limitations of dimensions. So we start our lecture. We start from physical quantities. As we know that in physics, we divide physical quantities in three major groups, that is base quantities, derived quantities, and supplementary quantities. Dimensions are defined with respect to base quantities. So we define dimensions. The statement of dimensions is as each base quantity denoted by a specific symbol. Each base quantity denoted by specific symbol and written within square bracket is called a dimension. And dimensions tell us about the nature of a physical quantity. As we know that every physical quantity has its own meaning. Every physical quantity have a different meaning, a different sense, different nature. So with the help of dimensions, we can know about the nature of a physical quantity. So this is the set of dimensions of base quantities. As we know that in physics there are 7 base quantities and all other quantities are the combination of these 7 base quantities. The base quantities are named as length, mass, time, electric current, thermodynamic temperature, intensity of light, and amount of substance. Length is measured in meters. SI unit of length is meters and its dimensional symbol is capital L. So dimension of length is written as capital L within square bracket. The unit of mass is kilograms and its dimension is denoted by capital M written within square bracket. If we simply write capital M, it does not mean that it is the dimension of mass. When we write capital M and enclose it in a square bracket, then it is read as the dimension of mass M. Time Time is measured in seconds and its dimension is denoted by capital T. Electric current, thermodynamic temperature, intensity of light, and amount of substance. These four terms, the dimensions of these four terms are denoted by the symbol of their units. Electric current is measured in amperes, its SI unit is ampere, and its symbol is capital A. So dimension of electric current is written as capital A within square bracket. Or sometimes in some books the dimension of current is written as capital I. Thermodynamic temperature is measured in Kelvin and its dimension is capital K. Intensity of light is measured in candela and its dimension is CD. It's the symbol of its SI unit and the symbol of its unit dimension is same. Similarly, the amount of substance is measured in mole and its dimension is also denoted as mole written within square bracket. These are some terms, that is, this is the dimension of temperature, this is dimension of intensity of light, and this is dimension of amount of substance. Sometimes these symbols are also used, but I personally prefer these symbols for the dimensions of base quantities. And in my further lectures, when I will derive the dimensions of derived quantities, I shall use these dimensional symbols for base quantities. Okay, next we talk about the sets of dimensions that are used in mechanics, electricity and magnetism, and in thermodynamics. In mechanics, all the physical quantities, base quantities or derived quantities, involve only these three terms: mass, length, and time. So the dimension for mass is capital M, dimension for length is L, and dimension for time is capital T. So this is the set of dimensions that is used in mechanics. In electricity and magnetism, mass, length, time, electric current, and intensity of light. These terms are, these physical quantities are used in electricity and magnetism. So the set of dimensions that is used in electricity and magnetism consists of the dimension of mass, dimension of length, dimension of time, dimension of current, and dimension of intensity of light. In thermodynamics, the set of dimensions consists of the dimension of mass, dimension of length, dimension of time, and dimension of temperature, and dimension of amount of substance. So this is these are the sets of dimensions that we use in mechanics, electricity, and in thermodynamics. Now we proceed further and we will discuss the dimensions of derived quantities and supplementary quantities and their applications and so on. Dimensions of derived quantities. As we know that derived quantities are combinations of base quantities. So the dimensions of derived quantities are combinations of dimensions of base quantities. For example, speed is defined as length over time. Speed is a derived quantity and it is the combination of length and time. Dimension of speed will be equal to the dimension of length and dimension of time. When we write a physical quantity in square brackets, it means that we are talking about the dimension of that quantity. So this is the formula of speed and this is the dimensional formula of speed. So the symbol of speed is written as V, and dimension of speed is equal to dimension of length capital L over dimension of time capital T. And finally, we write answer in one square bracket. So this expression can be written as dimension of speed is equal to the dimension of LT inverse, dimension of length and time. We read it as LT inverse. Dimension of acceleration. Acceleration is defined as velocity over time. So dimension of acceleration is equal to dimension of velocity over dimension of time. Dimension of velocity is calculated as it is written here. So it is equal to LT inverse over T. This term that is in the denominator, when it comes in numerator, its the symbol of its power is changed. So acceleration, the dimension of acceleration A is equal to LT inverse. This term was in the denominator. When it comes in numerator, its power, sign of its power is changed. So for every physical quantity, the final answer of dimensions is written in one square bracket. So we combine these two brackets, it will become L T inverse T inverse. These powers are added, so dimension of acceleration is equal to L T's power minus 2. So this is the dimension of acceleration. And acceleration is a derived quantity, and its dimension is the combination of dimensions of base quantities. Length and time are base quantities. Here is an other example of derived quantity and dimension of that quantity. By Newton's second law, we define force as F is equal to ma. Dimension of force is equal to the dimension of mass into dimension of acceleration. So dimension of mass is capital M, and for acceleration dimension is L T's power minus 2. And finally combining these two brackets and having we write it in one bracket, final answer is the dimension of force is ml T's power minus 2. Force is derived quantity, its dimension is the combination of base quantities. Mass, length and time, all these three quantities are base quantities. Now we talk about the dimensions of supplementary quantities. We have divided the physical quantities in three groups: base quantities, derived quantities and supplementary quantities. And we have discussed the dimensions of base and derived quantities. And now for the dimensions of supplementary quantities, here is. There are two supplementary quantities. One is plane angle and other is solid angle. The unit of plane angle is radian. This is SI unit, and SI unit of solid angle is steradian. Plane angle is a two-dimensional angle and solid angle is a three-dimensional angle. Both these physical quantities have no dimension. Plane angle have no dimension and solid angle also does not have any dimension. The quantities that have no dimension are called dimensionless quantities. Every physical quantity has a dimension. In physics, only these two quantities, which are the physical quantities, only these two physical quantities does not have any dimension: plane angle and solid angle. So we now we discuss how these quantities do not have dimension. So first of all, we talk about plane angle. Plane angle is a two-dimensional angle, and we define plane angle as plane angle is equal to the ratio of arc length of circle divided by radius of circle. If we mark 2 points on the circumference of circle as P1 and P2, the distance from point P1 to point P2 on the circumference is called the arc length of circle. So if we join the center of circle to this point P1, it becomes the radius of this circle R. Similarly, if we join the point P2 with the center O of the circle, this line also represents the circle of radius that is denoted by R. So if we mark these 2 points and we draw two radii from O to P1 and O to P2, then this is the arc length between point P1 and P2 denoted by L. So plane angle is defined as arc length between two radii, of circle. Okay, I reread it as plane angle is the angle between two radii of circle as shown here, angle theta, and we define it as arc length divided by radius of circle. Here arc length is denoted by L and radius is denoted by R. Angle is written as theta. So theta is defined as L over R. Dimension of theta, when we enclose it in a square bracket, it will represent the dimension of theta. So dimension of angle theta is equal to the dimension of length L and dimension of radius R. As we know that length is measured in meters and radius R is also measured in meters, length and radius both have same nature. Length and radius are quantities which are of same nature and they are measured with in same unit, that is meters. So dimension of length is capital L, radius is also length, so its dimension is also capital L. These two quantities have different name, but basically these are same quantities, that is length, and have same dimensions. So this term which is in the denominator, when it comes in numerator, its the sign of its power is reversed. So it is L and it becomes L's power minus 1. We combine these two brackets and it will become L's power 1 minus 1, 1 minus 1 0, so L's power is 0. And the term having its power 0 is equal to 1. 1 is a number which does not have any dimension. So we say that theta is dimensionless. And if we write its dimensional formula in terms of mass, length and time, we write it as dimension of theta is equal to dimension of mass in power 1, length in power 1 and t time in power 1. And all these terms are equal to 1, which means angle theta is dimensionless. So plane angle have no dimension. Now we talk about the solid angle. Solid angle is a three-dimensional angle which is subtended at the center of a sphere. Sphere is a three-dimensional geometrical object. So solid angle is the angle subtended at the center of sphere. And solid angle is defined as area of surface of sphere divided by square of radius of sphere. And if we have greater area, if we include greater area of sphere, we will have larger solid angle. If we take small area of solid sphere, surface of sphere, then the value of solid angle will be small. So we can mathematically in an equation write it as solid angle is defined as area of radius of sphere, its symbol is sigma, sigma is equal to a over r square. And for the dimension of this solid angle, we write the dimension of area and dimension of r square. Area has the dimension of L square. Area is defined as length into width. I have calculated the dimension of all physical quantities in a separate lecture. So how we calculate the dimension of area, for this you can see my lecture, and the link for dimension of area is given in the description. Okay, area has the dimension of L square and R is radius which is length, so its dimension is L. Due to square, its dimension becomes L square. And finally we can write it as L square, and when this term comes in numerator, it becomes L's power minus 2. And combining writing in one square bracket, we write L's power 2 minus 2, which is equal to L's power 0. So dimension of plane angle is L's power 0, that is equal to 1, which means that dimension of solid angle is none. It is a dimensionless physical quantity. and its dimensional formula in terms of mass, length and time can be written as mass in power of 0, length in power of 0 and time with power 0. So we have here discussed why plane angle and solid angle do not have dimensions. So the conclusion is that base quantities have dimensions, derived quantities have dimensions, but supplementary quantities do not have dimensions. Now we talk about dimensional analysis. So dimensional analysis dimensional analysis is a method in which we use dimensions to check the correctness of a formula or equation. With the help of dimensions, we can check correctness of an equation. And with the help of dimensions, we can derive a possible formula for a physical quantity. So this method in which we can check the correctness of an equation, validity of an equation, or we can derive a formula for a physical quantity. This method is called dimensional analysis. And we will discuss it at the end of lecture in detail. Note that the expressions of dimensions are manipulated as algebraic quantities. As in algebra, we can add, subtract, and multiply different quantities. Similarly, in dimensions, we can add, subtract, or multiply physical quantities. And as we know that same kind of quantities are added. Mass cannot be added into length, and time can never be subtracted from current. So same quantities are added. Similarly, the dimensions of same quantities, for example length or mass or electric current, so dimensions of similar quantities are added, subtracted or multiplied as we add, subtract or multiply quantities in algebra. For example, a physical quantity, that the dimension of length plus dimension of length is equal to 2 into dimension of length. Both these terms are similar, so these are added. Or we can write it as, we can take the example of division as dimension of L square divided by dimension of L is equal to dimension of L square, dimension of length square means L square into L's power minus 1, and it will be written as L's power 2 minus 1, which is equal to L. And in multiplication, we can write it as the dimension of L multiplied by dimension of L. L multiplied by L is equal to L square. So now we talk about some uses of dimensions. We can use dimensions as is told in dimensional analysis. We have talked about this use. We can check the correctness of an equation. So we can say that with the help of dimensions, we can check the homogeneity of physical equation. Homogeneity means we can check the correctness of an equation. If the dimensions on both sides of an equation are same, irrespective of form of formula, in which formula, in which form the quantity is calculated, it does not matter. If the dimensions on both sides of an equation are same, irrespective of form of formula, then equation is correct. This is called principle of homogeneity. As we know that uh, for example, we shall discuss it in our further. We will discuss these examples, but here as an example I can show you that force is written as F is equal to ma. Force can be written as F is equal to mv square over r. So formula does not matter. The dimension of force will always be same. So it is written here as, if the dimensions on both sides of an equation are same, irrespective of form of formula, then equation is correct. If the dimensions on both sides of an equation are not same, then equation is incorrect. This is called the principle of homogeneity. And with the help of dimensions, we can derive a possible formula. If we know, if we guess the possible factors on which a physical quantity depends, then we can derive the possible formula for that physical quantity. Both of these uses are discussed with example, will be discussed with example in detail at the end of this lecture. So, first we will talk about some features of dimensions. After that, I shall discuss the uses of dimensions in detail. Both of these uses will be discussed with examples. So here we are going to talk about some features of dimensions. Dimensions tell us about the qualitative nature of a physical quantity. Qualitative nature means about the nature of a physical quantity, as length is a different quantity, mass is a quantity of different nature. So dimensions tell us about the nature of physical quantity, or we can say that dimensions tell us that a physical quantity consists of which base quantities. Any physical quantity, for example, mass, length and time, these are three physical quantities having different nature, having different sense. So dimension of mass is written as capital M, dimension of length is written as capital L, and dimension of time is written as capital T. Whenever we see capital T written within square bracket, we can easily understand that it is about time. When we see capital M written in square bracket, we can easily guess that this is representing a quantity named as mass. So dimensions tell us about the nature of a quantity. For example, we in physics we talk about height, we talk about radius of circle, light year, diameter, and we know that height is measured in meters, radius of a circle is also measured in meters, light year is also measured in meters, and the unit of diameter is also meter. These quantities have different names. We consider height a different quantity, radius, light year, diameter. By name, by name these have different sense, but basically all these terms have same nature. That is, they represent length. Radius represents a length from center of circle to its circumference, to its boundary. Light year is a length, is a distance that is covered by light in 1 year. Diameter, that is also distance. So basically all these names have a quantity represent a quantity that is same in nature, which is length. So all these quantities are measured in meters and they have same dimensional symbol, that is capital L. So whenever we shall for height we will write the dimension L. Dimension of height we will write L. For dimension of radius we will write capital L, which means that these are different names, but by nature they are representing a same physical quantity, that is length. And here is an other example. As in physics we talk about velocity, we talk about instantaneous velocity, average velocity. All these terms have different sense, but by nature all these quantities are same. Velocity is defined as a rate of change of displacement, change in displacement over time. So its dimension is written as dimension of displacement, which is length, L, dimension of time. So dimension of velocity is LT inverse. Instantaneous velocity has the formula, that is limit delta t approaches to 0, delta d over delta t. Simply we talk about its dimension, that the dimension of instantaneous velocity is LT inverse, dimension of average velocity is LT inverse. So when we say velocity, average velocity, instantaneous velocity, we take these terms differently, that they have different meanings. But dimensionally, we see that all these three terms have same dimensional formula, which means that the nature of velocity, instantaneous velocity and average velocity is same. So the first feature which we are discussing is that dimensions tell us about the nature of a physical quantity. Secondly, dimensions do not tell about quantity of a physical quantity. And quantity means the magnitude of a physical quantity. For example, we write the dimension of force as F is equal to ml t's power minus 2. And force can have any magnitude. For example, force F1 has magnitude 10 newtons, force F2 has magnitude 15 newtons, and some force F3 has magnitude 70 newtons. Newton is the symbol of its SI unit, and Newton is written as kilogram meter per second square in terms of base units. And these units tell us that force consists of mass, length, and time. The dimensional formula of force F1 is ml t minus 2. For F2, dimensional formula is ml t's power minus 2. And for F3 also the dimensions are ml t's power minus 2. So these are three different forces having different magnitude, 10 Newton, 15 and 70. But when we see the dimension of F1, dimension of F2, dimension of F3, all these three forces have same dimensional formula. So it means that the dimensional formula just tells us about the physical quantity, that we are talking about force. But how much force is being exerted, what is the magnitude of force, dimension is not necessary for guessing the magnitude of a physical quantity. Okay, next, the dimension of a particular physical quantity do not depend on the mathematical formula that is being used for that quantity. One physical quantity may be calculated by different formulas. For example, area area of rectangle is defined as length into width. Length is a distance, width is a distance. Both are measured in meters. They have same unit, meter and meter. So when a physical quantity has the unit meter, it means that is length and its dimension is capital L. So dimension of area is equal to dimension of length capital L, dimension of width capital L, and that becomes L into L, L square. This is the dimensional formula for area, and we have calculated this dimension for the from the area of rectangle. And in case of a circle, area of circle is calculated from formula A is equal to pi r square. Pi is a number, and number is not a physical quantity. So this pi is dimensionless, and it is written as dimension of pi is represented with 1. Pi is number and it is dimensionless. R square, r is the distance, that is radius. It is measured in meters, which is length. So radius is length. Its dimension is represented by L. Due to its square, we write the dimension of radius square as L square. So dimension of area is L square. As in case of a rectangle, the formula for area is length into width, and in case of a circle, the formula for area is pi r square. We calculate area by different formulas, but when we calculated the dimension, we see that whatever formula for we use for a physical quantity, the dimension of a particular physical quantity remains same. Similarly, for the area of triangle, formula is 1 over 2 base into height. Base is measured in meters, length is height is measured in meters. So both are length. So dimension is a dimension of area is dimension of 1 over 2, dimension of base, dimension of height, which is L and L. 1 over 2 is a number and it is dimensionless. So dimensional formula for area for a triangle comes out L square. We used different formulas to calculate the area, but the dimensional formula of area is same. Or we can say it as area can have different mathematical formula, but the dimensional formula of area is same. We can discuss this feature with another example. We take the example of force. By Newton's law, force is written as F is equal to ma, and dimension of force is the combination of dimension of mass and dimension of acceleration. For mass we write capital M, and for acceleration we write L t's power minus 2. The dimensions of every physical quantity as acceleration, area or anything, for every physical quantity I have calculated the dimension in a separate lecture, and you can see all my lectures on dimensions for each physical quantity in physics. Okay, so combining these, we write the dimensional force formula for force as mlt minus 2. We can also write force in mathematical form as F is equal to mv square over r. It is for circular motion. And we calculate dimension of mass, velocity and radius, and finally we find that dimension of force comes out ml t's power minus 2. So whatever is the formula for a physical quantity, for same physical quantity, the mathematical formula may be different, but the dimensional formula is always same. Whatever is formula, The dimensional formula is same for a particular physical quantity. So this is very important feature of physical quantities. Next, we talk about the limitations or drawbacks of dimensions. So one drawback of dimensions is that with the help of dimensions we can derive a formula, but dimensions do not give any information about the constant of proportionality that may appear in the formula. Whenever we derive a formula with the help of dimensions, the constant of proportionality that appears in the expression, we cannot calculate the value of that constant with the help of dimensions because the constants do not have dimensions. When constants do not have dimensions, then we can never find any information about that constant with dimensions. So, to calculate a constant in a formula, experiments are needed for that purpose. Dimensions do not tell us about the magnitude of a physical quantity. This is one of the drawbacks which we have discussed earlier. And with the help of dimensions, we can we cannot derive a formula of physical quantity that depends on the sum or difference of other physical quantities. For example, I discussed it here dimensionally. We can derive a formula of the form as in which a physical quantity depends on other physical quantities that are being multiplied. For example, if x, y, and z are three different quantities on which this physical quantity depends, and if the formula of this quantity depends on these quantities in such a way that these quantities are being multiplied, then we can derive the formula for this physical quantity with the help of dimensions. But when a formula consists of sum or difference of two or more physical quantities, we can never guess the correct form of that formula with the help of dimensions. For example, by second equation of motion, we calculate distance as the formula of distance is s is equal to ut plus half at square. If we write the formula for distance as s is equal to ut, or I write the formula for distance as s is equal to ut plus half at square minus ct. All these forms have same dimension. This equation is dimensionally correct. This equation is also dimensionally correct, and this equation is also dimensionally correct. So all these terms, all these expressions have the dimension of length. You can calculate the dimension of these expressions and you will find that all these equations have same dimensions. Sorry, uh, I correct this sentence and this term as the distance s has the dimension of length and dimension of length. So dimensions on left hand side of this equation and dimensions on right hand side of this equation are same. So all these relations are dimensionally correct, but only this formula is correct in physics. these two expressions are not accurate. So if we want to derive a formula for distance with respect to with the help of dimensions, then we will reach for the formula of distance as dimension of L, but uh, that formula contains two terms or three terms. Dimensions will not tell us about that. So with the help of dimensions, we can derive only those formulas in which physical quantities are being multiplied, in which the quantities are being added or subtracted. For that kind of formulas, the dimensions can never help us. So, this is all about dimensions. In the next lecture, I shall discuss about the uses and applications of dimensions in detail. With the help of examples, we will discuss the uses of dimensions. So this is end of our lecture. For the dimensions of other physical quantities and for the dimensions of all physical quantities, you can follow my channel, and you can subscribe my channel so that you can get updates about dimensions.